All right, let's go back to the Python library, sorry, Python setting to do the same thing we did on our Excel file. The bunch of data. Let me go back to the advertising dollar here. So, we can do the same thing on a Python library here. And a regression problem is the idea that it is supervised in the sense that we've already told some ideas of functions of each variables already given, already annotated, already labeled. So that is what we call supervised learning, when we're actually explicitly told for a sample of data, this is what's going to happen now. Based on that, tell me what's going to happen in the future. Unsupervised is we're not telling anything to do to the machine, it actually figures it out. So an example of supervised learning could be hospital data for someone who had COVID. Did they follow, were they unwell? Did they die? Did they survive? Those are some labelings where we can give. In other words, we can just give the data without labeling anything, their blood pressure, their sugar level, and based on that, machine will automatically tell us who passed away and whatnot, right? It will cluster it in some areas. Linear regression is used almost everywhere. It's one of the oldest models, and it's one of the most introductory models that you'll see in every space. So it's always good to use. Linear means aligned. And then, like I mentioned earlier in my other video, we're trying to draw a line to ensure that we somehow create a function or a model based on the coefficient and also slope, right? The libraries, we leverage stats model. So a lot of stuff that you've already used, like Pandas, Seaborn, sklearn is quite common, NumPy, so forth. In this one, we're specifically calling linear regression. You can throw as many as you want in here, as long as you're not, even if you don't use it, it won't give you a problem, but it's always best to organize it as well. So this function here allows you to see the plots in line when you run the data, but most of the stuff you've already done. The new thing would be these guys here: import stats model, SMF, formula, linear regression. There's a specific purpose for that, as we'll speak throughout the course of this lecture. So let's run that. And one thing I wanted to point out maybe is that when you're opening a notebook, sometimes it could be conflicting. So maybe the best way, I'll do it again, is that restart kernel and clear outputs of all cells. So it's actually sometimes good just to clean it up so that there's no outputs here, and you don't feel like you're confusing with the previous year on model. It's always a good practice sometimes. So let's run it again. And we're here now. And this is where we're importing the data, advertising.csv. If you go back to your folder and import the advertising.csv, it's going to be here. One thing to note is, let me first import the data. So data using Panda and reading CSV. If it was Excel, it would be something else in here and so forth. Make sure this data is under the same folder as your the file. If it's not, you'll have to explicitly define the path, but it's slightly complicated, so I'm just going to use this for now. So head gives you information, right? Like data.head, TV, radio, newspaper, sales. These are in like indexing within the Python environment, so you don't need to care about these things, but this is what it is. So if you wanted to find sales, you can use newspaper, radio, TV. If you wanted to find TV expenditure, you can do radio, newspaper, and sales, whatever it is. This is response or dependent variable. These are features or independent variables. So you can use any terminology if you wish. So, same thing we're talking about here. You could also do, go like this, print, if you didn't know, the number of columns. So you could do data.columns and hit run again. It will do the same thing. And you'll say, okay, there are 4 columns and these are the data types. Same thing here, delete it. So what we're trying to do now is, again, I'm going to data.head and we'll do this again, just to kind of get an idea. So what we're trying to do with this next code is we want to see, let's say we want to figure out sales, right? And then the sales, we want to know how it relates to newspaper, radio, and TV independently. So essentially, what we're trying to do here is something like this. We're trying to put sales in y-axis, and the other guy is in the x-axis. So it'll be newspaper for one, and then it'll be TV for the other, and so forth. So in linear regression or in machine learning or statistical modeling, y is the desired value, y is your variable of interest, y is your dependent variable, y is your response variable. So on y-axis, we're always going to put whatever we want to find out, is always the case. X is the things that is going to explain how y or what value of y you can have, right? So in this particular case, what we're trying to do here is, erase this here, is going to use seaborn pair plot. Pair means two different variables, and it is telling you that use TV, radio, and newspaper independently and compare it with sales. Okay, so and then I will run the chart here, and now what you see here is on x-axis sales, y-axis TV, sorry, x-axis TV, radio, and newspaper. And as you can see, it looks like if you just notice it, this guy, the TV, is more correlated because it's snug, and then also it's not scattered, right? If you draw a line here, something like this, this model was going to be attractive. So when we draw a line, you have to make sure that every little bubble is captured and there's less residual. So we do this, and if you do this, out of these, this is probably the best correlation. They're very similar in their movement. Second is probably the second best, and the third is looks like it is all over the place. So very quickly we could find a correlation. We can also find numerical value, but just visually it's amazing. Now, if you wanted to find sales, we're always looking at it from a Y point of view. What is Y? What is sales? So let's say Y is sales. And for you to find sales, you need to find y-intercept and beta 1 coefficient times x. What does this mean? I'll go back to the chart here. Let's ideally look at this, right? Like, let's say, let's draw a line. So, we're given this data. We did it sales and TV as y and x-axis, and we drew a line. So the line can go to perpetuity. It can go forever, but we only have data until this point, like 325. So if someone says, I want to know what the sales is going to be like when the TV dollars is, let's say, 500, then what we'll technically be doing is we're going to follow this line and we'll see where this line intersects, probably somewhere here. So we'll probably say the sales is somewhere around like 30, ideally, right? So this is what we call observed, meaning we know it's historical data. And this is what we call is predicted, right? We're predicting based on the trend. Now, think about it. Y-intercept is this number close to 5. It is intercepting or crossing Y. It could also be negative if it continues to go down. What Y-intercept is telling you is that if you did not put any money on TV advertising, what's the bare minimum sales? So the bare minimum sales is 5. Of course, right? Because what if you don't put money on TV? There's still radio contribution, still newspaper contribution. So sales has to be there. It doesn't stop. So what's the minimum money if the TV is 0, which is this function here at the bottom? I'll show you in a bit. And then rest of it is function of TV. What kind of impact does TV have? So let's go down here. I apologize if I'm like confusing you more, but this is slightly difficult concept to grasp, but once you get it, it's so here. Now this is the function. So y sales, y-intercept, and some weightage of some influence of x. What is the influence of x? The influence of x is determined by coefficients right here that is going to be extracted. We'll talk about that in a bit. So let's go down here and let's run the model here as we speak. So what we're doing here is we're creating a model called LM1 all the way at the bottom. And this is a function, ordinary least squares function, which is one of the ways to draw a line. So it's always drawing a line. And the formula says equals sales explained by TV, and they say data equals data means grab data from the data is equals to data, and dot fit means draw a line. Very simple. If you wanted more, you could add more functions, but it's just called simple linear regression. So let's run that. And it is giving us 6.97 and 0.045, 0.055 rather. So let's look at the function. What the function is telling us is sales equals 6.97. So 6.97 stands for if there was absolutely no money invested through TV, what is the bare minimum sales? It is going to be 6.97. After that, we'll be doing 0.05 times, let's say if we put $10 in TV, what is the sales going to be? So if you deduce the function, like, it'll be 6.97 plus, I think, 0.5. And if I'm doing this correct, it will be 7.47. So as you can see, there is function that is base or constant, and there's influence of this one. So if this guy was, let's say, 0.9, your function will totally be different. It will be like 9. So it will be, it will be more like 15.47, right? So this is a big function. So very, very quickly, you can tell that TV does not have a big of an influence that we thought. Very slight influence, right? Now we can also do all the columns, right? So in this case, we can also, this is a slightly different way of doing things, but essentially what we're saying here is so for example, as opposed to doing it this way, we can also say X features equals TV, and then we can always do comma equals sales if you wanted to, right? Some not sales rather, but newspaper. And you can create a column like this, or like this is just to kind of make it more efficient. So it does the same thing. Features equals columns, you can add it. It's a placeholder. X feature column is referring to TV, and Y is referring to dates, sales, and linear regression is the function to call, and it is saying fit and print the coefficient. This is a stats model library. This is a scikit-learn library. You can choose any way. It doesn't really matter. Technically, it should give you same value roughly, if you notice that. So if you're using Python, you probably use scikit-learn more. If you're using more R kind of concept, stats model is from R programming. Some people like to use it. You choose what's good, right? So in other words, the number here is slightly inaccurate. It should be 0.05547. But essentially, what I am telling you here is that a unit increase in TV is this value here. The data changes, obviously the value changes. And if you are additional $1,000 spent on the TV would be, you got the answers correct, 1,000 times this value, right? Whatever it is, right? So, as you can see, the number is not accurate, but this is because the data changed a little bit. So, you can do a manual calculation, just I showed you in here, something like the thing. And this also works as a calculator. So we can just go here, 6.97. 6.97, and then the coefficient is here, and let's say you put 50, and we're saying 50 because everything is normalized to 50. 50,000 is 50. So let's hit that run, and obviously something is, yeah. So I had this thing here. Let's run it again, and it is 9.75. Ignore this because coefficients always changes depending on the data, right? That's not the intent. We can also randomly give a value. For example, let's say we wanted 50, same thing, But as opposed to manually calculating this, we can create a new data frame, and you can use the old model, LM1, this model, to predict a new value. So if you had 5,000, you can just plug like 5 million or whatever, and then just run it here. And it is telling you the sales is going to be that. If you do 50, which we know the answer, let's run it. It should be 9.774. Okay, so this is just a way to simplify things, right? Again, same thing. We can predict using the 50, which is again the variables. Obviously, everything is 1,000, so you can always look at the value. So how do we plot the line, right? So look at this plotting of the line here, and let's run it. And the line itself, the one I'm talking about, it always goes through the intercept, although it may not look like it. But this is the best line because it ensures that most of the bubbles are captured. Although it may not look like it here, this is the best case scenario, right? And it does a lot of different calculations before getting into this line. It tries to minimize the residuals. So in other words, what it does is these are if the line does not cross the bubble, these are inaccuracies, right? All of these are inaccuracies. So it ensures that collectively it is least inaccurate. Collectively, the sum of all residuals, positive, negative, is low, right? So although sometimes it may not look like this line is the best, it has done its mathematical foundation. The range here, the shaded line, is your confidence interval. So upper and lower case scenario, right? So this is also going to be, things like that. So what we define, confidence interval, usually it's used at a 95%. It is that if we draw it 100 times, we would be correct 95 of the times. That's what we think. That's a confidence that's given to us. So we can also grab the confidence interval, just like this, from the model here. And then you can also look into it from a point of view. So we'll keep on going here. The hypothesis testing is also another technique that we can try to see if it makes sense. Is the hypothesis testing is, for example, you have two conditions, and either you accept the condition or you reject the condition. So think about this. Let's establish a null hypothesis. We created a model that the sales was explained by TV. We think there's a relationship. That is why we created that model. But who's to say that there is a relationship? So we start with something called, we want to dispute that. So we establish a null hypothesis that says there is absolutely no relationship between TV ads and sales. In other words, if this guy, B1, the coefficient, I'm going to go a little up. If this guy, B1, we think it's going to be 0. It's closer to 0, but we think it's absolutely 0. It is not negative. It is not positive. It's absolutely 0. Alternative is opposite, exactly opposite. These are competing. They compete with each other. So either we have to accept that there's a relationship, or we dispute or reject that there is a relationship. So how do we test this hypothesis? We can use a confidence interval, right? Confidence interval or the p-value. And what it is that, let me draw a little bit of a diagram here so it makes sense. So, we'll essentially, if there's something's distributed, what we're saying here is if this has no relationship, it stands here, let's say. And if it has relationship, it will go into this zone. So essentially what confidence interval is telling you that it is going to be in a certain zone, right? So that is also one way of doing things, right? So let's look at the p-value here. And the p-value is extremely small. So I might have rushed here. So let's say, you try to do these things here, null and a hypothesis. And what this tells you is that, if there is no relationship between TV and as, the coefficient is 0, and alternatively, it is more or not equal to 0. It could be negative or positive, right? So we extract the p-value, LM, the p-values of both coefficient. And we decide that 95% confidence interval is our factor. Like typically, it's always 95%. So 95% equals to 0.5 p-value. Always, right? 1 minus 95, it's 5%. The way to look at it here is that the intercept is a very small value. This is like very, very, very small value. And this is also very, very, very small value. It's a lot less than anytime you see like dash 54, it means like 0.0054 times. So let's look at it. Null, it says, let's compare 0.05 or TV value here. Which one is bigger? This is bigger and this is smaller. So if this is smaller than this guy, then we reject the null and accept the alternative. For us to accept it, this guy needed to be like 0.06, for example, right? So that is one way of we're doing the hypothesis testing. I'm just going to delete that for here. We also want to know how well this model does, right? Like, we talk about R square, adjusted R square. We can look at it. It ranges from 0 to 1. And if it's closer to 1, it's great. If it's closer to 0, it's not great. So let's look at the LM1 squared. And it looks like it's a decent model. It's 0.812. It means that it is able to explain data 81% of the time. What it means by explain is it's all understanding the trends, the biases, and variance in the data. Same, let's look at the other model, LM2. From scikit-learn, it should have similar R squared. And here I'm doing it, every time I'm doing a different technique. You can choose one. There's no good or bad. It was just showing you different models, right? Now we can also look at TV, radio, and newspaper, all of them together. And all we're doing is using this plus button, plus radio, plus newspaper, and so forth to look at the parameters. Nothing changes. And obviously, if you wanted a function, 4.6. So you can see the best influence is radio. Radio has a big influence right away. Same thing with scikit-learn. We're just adding radio and newspaper. Look at the coefficients. Boom, same thing, 4.62. It is a slightly different way of looking at things. You can also pair the feature names with coefficients. Let's look at it. And in stats model, there's something called summary function. I am moving a little faster here, but it's same thing if we're just doing pretty much different thing. So the summary function is cleaner. So, it can give you a lot of different information very, very quickly. Let me erase that little thing here. So essentially, it's telling you dependent variable is cells. You're trying to find cells. Adjusted R squared is 0.90. I'll ignore this for now. The lower, the better these values. Degree of freedom means 200 minus 4 variables, 196. This is the technique it's using. This is the method it's using. This is the date it was called on. And the confidence interval, the coefficient is 4.62 at a 95% or 90. Like there's a different ranges here that you can use. And this is something we'll ignore it for now. But you can typically look 4.62. So for example, if you wanted to create a model, sales, the model is telling you that it is going to be 4.62 plus 0.05 times TV plus 0.10 times radio plus 0.003 times news paper. Right, so this is the function that you can manually calculate. So that's what's happening. Your sales model, and how do you know this model is good? The adjusted R square, and the R square is showing is above 90, which is pretty decent model. Okay, so you have worse chance of being wrong. So sometimes you can also look at the feature selection. How do we know which feature is good? So you can technically, there's a lot of different techniques, but I just want to figure, let's look at this one, right? So it had all these TV, radio, newspaper, and the adjusted R square came about 0.90, and or R square came around 90. And let's just use TV and radio, see how it does. And it actually was slightly better, 0.90 to 2. So the thing is, you probably don't need newspaper, right? Again, let's run that. So this looks like now it's kind of similar. You can know the difference, 2589. So this is slightly different. So if it looks like this is okay. If you did just this guy here, just TV, is this going to be good or bad? Let's look at it. It's 81. So the thing is, you have to understand that just if you could think about this way, right? If you could make just one friend, and the friend was able to help you out every assignment in the class, you don't need a lot of friends. I'm just trying to be a little cynical here, because the other friends are just too intensive, it's too resource intensive for you. They have to talk to them, you have to do stuff. So same thing like in data, right? The less feature, the better, because computing wise also it takes a lot less resources. But ultimately our goal is to make the model like very accurate, and eventually if it's accurate, it is going to add a lot of value, right? There are other techniques that we can use, are called mean absolute error, mean square error, and so forth. And what this is telling you us is that if this is the actual value, 100, 50, 30, 20, and if this is a prediction, give me some metrics, mean absolute error, mean square error. And these are, what the means is that, let me run that, means that the lower the better. So is 10, 150, 12 good? We don't know until we have multiple models and we can compare, right? So we can always, let's, so let's, you can try different numbers here. And this is, I'm just going to copy this here just so that we don't lose track of it. And let's put this here. And then if you do highlight it and put, backslash, oops, what happened there? And copies, okay, never mind. I think I lost it. Okay, return to. Okay, never mind. So you can always look into this function, right? So same thing here. TV, radio, and let's look at the mean square error here. Run it, and 1.50. So looks lower the better, which is not a bad idea. Let's look at a different model with this TV and radio. Looks like it is kind of similar. This is better because it is slightly lower. So it means that the error is decreasing, right? We can also look at the managing the categorical data. And so far, if you look, we all care. The only thing we cared about is just looking at it, just gonna numerical data. But we can also incorporate categorical data, which I will be covering in a totally different video. So let's wait until we get there. But at this point, you should be able to run linear regression using either scikit-learn or stats model, and should be able to import the data. The second part of it, which we'll be doing using categorical data, I'll make a separate video so that it doesn't compete with this one. All right, thanks a lot.